Okay, so good afternoon, everyone. So today we are going to do the tutorial exercises for Quadrature. So remember, because we lost one tutorial due to Good Friday, so this week we do Quadrature. Next week, initial value problems, and the last tutorial will be in week 11, Monday, week 11. Okay. So now for Quadrature. So remember, so we have here a composite integrals. Yeah. So what is a midpoint rules? And you want to evaluate this integral, for example, and then you want to estimate how many subintervals you need so that the following integrals will be approximate with the absolute errors less than 10 to the minus 4. Okay, so if you remember what is the midpoint rules, so the midpoint rules look like this. So let me draw pictures. Yeah. So the midpoint rules is you have, so this is my function. So I integral from 0 to 5. Yeah. And the function maybe look like this. Yeah. So the midpoint rules say, okay, so suppose I divide it into only 4 subintervals. Okay. So the midpoint rules, I take the midpoint and I draw the rectangles. Yeah. So the midpoint, then I draw a rectangle. Midpoint, I draw a rectangle. Midpoint, draw a rectangle. Draw a rectangle. Then I will sum up on the area. Okay. Under the rectangles. Okay. So that is a midpoint rules. So, but we are interested in the errors. So if you go back to the lectures, you will see that the errors of the midpoint rules, the composite midpoint rules, yeah, is given by, so now if I take the lecture notes, yeah, so the midpoint rules will be given by, so if you go to the lectures, so the lecture note, yeah, and topic 6 quadratures, and you will see that for the midpoint rules, okay, let me show you what is the errors. So the errors will be, so the midpoint rules, so these are trapezoidal rules, yeah. So this, the midpoint rules is, so it's given here. Okay, so this is the sum of on the areas of the rectangles. You take the width to be hj and the height to be f of the midpoints, yeah. And so the errors in this case is b minus a over 24 f double prime h square. Okay, so that is the formula, right? So this one can be proved, like by Taylor expansion. Yeah. And now I'm going back to the problem. So now I'm going back to the problem. And so this is the errors, yeah. So now what I want is, I want these errors to be less than 10 to the minus 4, yeah. So now first we have to estimate this. So we know b, we know a, so b just 5, a just 0, and h square is just the width of the intervals. But now we need to know the estimate for f double prime. So remember what is the function? So the function will be, so in our case, the function will be f is just equal 1 over 1 plus x minus pi square. Okay. And now I want to know what is the max of f double prime in absolute value over the interval 0 to 5. So this is a calculus problem, and I'm a bit lazy. So suppose I put in Maple TA, or sorry, in Maple or in Wolfram. So suppose I put in Wolfram, yeah. So see whether we can find this maximum easily. So suppose I'm going to use Wolfram. I mean, you know, first year then you use calculus, but then now you are in second year already, so you can use Wolfram, you know. So let me share with you the anyway. Did anyone get a maximum value of this derivative? So first we have to find the second derivative. Okay, so derivative. Okay, so the second derivative. So we need the second derivative. Yeah. So second derivative of 1 over 1 plus x. Oh, sorry. So what happened? Okay, so 1 over 1 plus x minus pi square. Okay. So what is the second derivative of this one? And it's a bit complicated, but you can get it. So x minus pi square plus 1 cube minus 2 over x minus pi square plus 1 square. Okay, so you can see a plot like this. So this is a plot from 1.7 to 4.6, yeah. And we're interested in, so maybe this one is a more compact form, yeah. So 6 over pi minus x square minus 2 over x minus pi square plus 1 cube. Yeah. And now what I want is I want to see what is the max value of over the intervals 2. So they have a global maxima. So the max is 1/2. And the global maximum. So the second derivative is just less than 0.5. Well, okay, so we need a local, yeah. So now suppose I take max value of this one, max value of over 0 to 5. See what is the results. Okay, and so it seems that The max is 0.5. Okay. No, but actually what we want is we want the absolute value. We don't want the we don't want the value, but we want the max absolute value. Yeah. As you see, the absolute value can be bigger. No global. Okay, so maybe we see the plot again. Yeah. So what I want is not only the max value, but in this case we want the mean value as well, right? Because what we want is the maximal in absolute value. So if you take a positive than 0.5, and if I take the mean, then will be -2. Yeah. So so in absolute value, it will be less than or equal to. Yeah. So I'm going back to the notes now. Yeah. So we are a bit lazy. So we use a Wolfram or Google, and we say that, okay, this one less than or equal to over 0 to 5. Okay, so you can use calculus or you can use the internet, okay, whatever. So now what I'm going to do is I'm going to plug it in the errors. Yeah, so I say that, okay, my errors will be, so the absolute value of the errors will be minus a, maybe 5 minus 0, so just 5. Yeah, so 5 minus 0 over 24 f double prime c h square. And I know this one, you know, I mean the maximal value is just 2, right? So 5 multiplied by 2 over 24 h square, right? And what is just 10 over 24 h square, right? In absolute value. And I want this one to be less than 10 to the minus 4. Yeah. So if I want this one less than the minus 4, then I just need to solve h is just less than 24 over 10 to the minus 4. I mean h square. Yeah. And we have to take the square root of this one. Okay. So what is square root of 2.4 10 to the minus 2? Okay. And then what is the number of intervals? So the number of intervals will be, so m will be, you know, you take what is the number of intervals? So the number of intervals is just b minus a over h, right? Because h is b minus a over m, so m is just b minus a over h, so it's 5 over h. Okay. And because it could be non-integers, maybe we take a rounding of this value. So you got 5 over square root 2.4 10 to the minus 2. So it will be, take the rounding value. Then you get so 323. Okay, so you need to divide it into 323 subintervals in order to get that small values of errors. Okay, so you can do the same for other functions. So it just become of, you know, how you find the maximal value of the second derivative. Okay. Yeah, so here, you know, first you have to take the function f and you take the second derivative and take the maximal over the domain you want to integrate. So then you put it in the formula and you get out the estimate. Okay. So that is question 1. So how about So any question? So no question, yeah. Okay, so now the next question is Richardson extrapolation. So Richardson extrapolation is a formula, okay, discovered by Richardson. He's a British mathematician living in the 19th century up to the middle of the 20th century. And one of his contribution to mathematics is this formula, okay? So you can discover some formula and you wait 100 years and somebody will call the formula after you, yeah? So now what it is suppose you have two approximation of the integrals, okay? I1 and I2. Then you can define a new approximation, okay, based on this formula. And then this approximation will be better than I1 or I2. So what does it mean? It just means that, okay, if you take IR, you minus the exact integrals, then it will be, the errors will be smaller than I minus I1 or I minus I2. Okay, and you will see why. Okay, so we have to prove it. So in order to prove it, first we have to, you know, like remember what is the errors of the trapezoidal formula. So if you go back to the lecture notes, yeah, so the trapezoidal rules, the errors will be of this form, yeah. So the errors of a trapezoidal rules minus b over a minus, sorry, b minus a over 12 f double prime c h square, okay. So for trapezoidal rules. So now I'm going to show you that. So suppose you take a trapezoidal rule with step size h1, yeah. So then you got something like I1, okay. So what is I1 in terms of the exact integral? So remember now you have exact integral is I, is integral of f from a to b. Okay. So now the error say that, okay, so if I take the exact integral minus the quadrature, okay, so remember this is a trapezoidal rules, yeah, so trapezoidal rules, yeah. Then by the formula it will be minus b over a over 12 f double prime c h square h1, yeah, because I choose a step size to be h1, yeah. So I got this formula. Or, you know, I mean, I can write down I equal I1 minus b minus a over 2 over 12 f double prime c h1 square, yeah. So c is something between a and b, okay. So c is between a and b. But now let me expand this term in terms of Taylor expansion, right? I can expand this one using Taylor expansion for f double prime. So I can write out, actually this one is f double prime of a plus h1, yeah, f triple prime, right? Because you can use Taylor, or you can use mean value theorem for f double prime, yeah. So you can write out like this, and still b minus a over 12, still I1 here, I here, yeah. And then do not forget the h1 square still outside, still stay outside, yeah. Then the equation can be written in a simple form like this. So it will be C1 h square, h1 square, right? Because if I take this, I multiply out, yeah? Then I relabel everything to be a constant. Then it's just a constant C1 multiplied by h1 square, yeah? And then, you know, I mean, the next term will be something of order OH1 cube, okay? I mean the big O notation just means that it's a constant multiplied by h1 cube, and you can see the constant just come from this, yeah. And now I can do the same for quadrature of step size h2. Okay, so I can have very similar, yeah, but now it will be h2 square. And remember, the constant doesn't change because the function f doesn't change. Yeah, so b and a doesn't change, so that's why the constant c1 here is still the same when you change h1 to h2. Okay, so plus OH2 cube. Okay, and I label this one is number 1 and this one is number 2. So now let me multiply multiply equation 1 by h2, well, by h2 square. Okay, and then I minus equation 2 multiplied by h1 square. So why I'm doing this? Well, you will see that this term will get cancelled, right? Because if you multiply by h1 square, multiply h2 square here, and then you minus h1 square, h2 square here, then it just goes away, right? And that is exactly what I'm going to do, yeah? So I'm going to take number 1 will be I of h2 square minus h1 square, okay? And then I have h2 square I1 minus h1 square I2. And this one goes away, right? And now you see, now if I multiply 1 by h2 square, right? Then I got h1 cube multiply h2 square. But if I take h to be the maximal of the 2, then I just have something like OH5. Okay, so h is the max of the 2 value, h1 and h2. Okay, so roughly it will be OH5, yeah. And then I just divided, you know, so if I take I will be I divided by h2 square minus h1 square. You know, so h2 square I1 minus h1 square I2. Yeah. And you see I divided by h square, you know, so this one will be order OH cube. Okay, so remember h is just the maximum of h1, h2. And you see now if I label this one, the new terms here is IR. Yeah. Then you can see that I minus IR is of order OH cube. Yeah, what is better than OH square? Remember? So before you have some approximation of order OH square, and now you have something order OH cube. So therefore IR is a better approximation. Yeah. So any question? Yeah, so there's a question. How do I come up with the Taylor series like that? What Taylor series? Well, this one is just well, maybe not Taylor series, but mean value theorem. I mean, if you go back to this, you mean this line or what? This line? Well, I mean, you just apply mean value theorem for f double prime. over the interval AB. Yeah, so I can do that, right? So I mean, you take a point f of x, then f of x is f of a plus h times f of x minus a, f prime x minus a. So essentially it's just the same. Mean value theorem or Taylor theorems. Yeah. Okay, so everything is okay. Yeah. So now, actually, I mean, you look at IR. Yeah. And you say, wait a minute. Well, actually, it's not exactly the same as in the question. So why I claim that is IR? So now if you look back at the question, okay, then the question is IR is given like this, okay, not in the form that I wrote down. Well, but actually now we have to do some transformation. So let me start with this formula and see whether I get exactly the same. So now let me start with, let me copy down the formula in the question. Yeah. So now suppose I copy down IR is I1 plus I1 minus I2 over H2 over H1 square minus 1. Yeah. Then now okay, so this is the one in the question. So now I just multiply by H1 square. So I multiply by H1 square. Then I just have H2 square here minus H1 square, right? And then I multiply by H1 square here minus H1 square I2, right? And now let's make they have the same denominator. So I have H square 2 minus H1 square. Yeah, so then I multiply, so I1 H2 square minus I1 H1 square and plus H1 square I1 minus H1 square I2, right? And you can see that this one get canceled. Okay, and then you have exactly what I wrote down before. So I1 H2 square minus H1 square I2 over H2 square minus H1 square. So it's identical to the formula I wrote down before. So if you compare, yeah, so they are the same. Okay, so we show that, okay, it's possible to find out something more accurate than I1 and I2. Okay, but just we don't have to do the evaluation of the integrals again. And you see, I mean, suppose the function is very complicated, then this one will save a lot of time. Yeah. So now we try to verify it by the, so the next question is we verify whether it's correct by the following example. Okay, so suppose you have this integral. Okay, so 0 to 2 e to the minus x squared dx, use trapezoidal rules, and then verify that IR is a better approximation. Okay, so now we have to do it by MATLAB. Okay, so because you can do it by hand, but I think it's not very efficient, so we do it by MATLAB. So suppose I share with you my MATLAB screen. So remember we have a file called Simpson, right? Simpson.m. And remember we have something like this. Yeah, so for the previous lab, yeah, so we implement the 3 quadratures at the same time, Simpson midpoint and trapezoidal rules. Okay, and the question now say that use trapezoidal rules. So now what is the function? Well, the function is exponential of e to the x squared, right? And now you have integral from 0 to 2. Yeah. So now what is the exact one? So we don't have this anymore. Yeah. So we assume that we have an exact value. Okay, is given by, so given by this. And so there is no formula for, no closed form for the antiderivative. So we have to use numeric values here. Yeah. So now if I put h to be 1, so h1 to be 1. So you see h1 to be 1, yeah. So you can do this by hand, yeah. But suppose we lazy, so we just use MATLAB. So Simpson here. So now you compute Simpson with the first partition, yeah. So you got x1 here, and now we don't have to print out here. And then after that, you reduce h1 by half. So you got h2 is 0.5. Okay, so 0.5 is, now you have 4 subintervals. Yeah. So S M T2 is Simpson with respect to, well, we have to implement the partition. Yeah. So the partition will be with respect to H2. Okay. And now I have Simpson. Well, remember Simpson, but actually it's computer trapezoidal rules, yeah, because it compute three rules at the same time. So I just use the trapezoidal rules, yeah. So now the errors. So now the errors, as error 1 will be absolute value of exact minus I1. So I1, sorry, T1, yeah. And error 2 is absolute value of exact minus T2, right? And now we have to define the Richardson extrapolation. So IR is I1, well, I1 is T1 H2 square minus H1 square T2, and you divide it by H2 square minus H1 square. Okay. And now error R is absolute value of exact minus IR. Okay. And now we run it. So we run it. So we run it. So what is the problem? Okay. So this one is, should be a dot. So unrecognized X2. Okay. So this one should be X2. Okay. So save it. So you can see that. Okay. So if I use the, Simpson rule, sorry, not Simpson, I use a trapezoidal rules with h1 equal 1, then I got the errors is 0.005. Okay, and when I reduce h1 by half, I got 0.0015. Yeah, but the Richardson give you the errors is 10 to the minus 4. So you see, so you see the improvement. So the errors is much better. Okay, and you don't have to compute the quadrature rules again. Yeah. So any question for that? So that is the idea. So we prove it, and then we test it, you know, by the example, numerical example. Okay. And now go back to the problem. So what is the next problem? Okay, so now the next problem is kernel for the rules of precision R. So this one I did in the lectures already, and it's also in the lecture notes. So please either watch the video or go back to the lecture notes. Yeah. And we do the calculation for trapezoidal rules as well. Okay, so I'm not going to repeat it here. And the midpoint rules, we did it in class, I mean in the lectures as well. And Simpson rules, okay, we haven't done that, but the calculation can be found in the lecture notes. I can show you. So if you go to the lecture notes, yeah, so you can up to Simpson rules. So this is the Simpson, no, not. Okay, so this is a calculation for Simpson rules, the piano kernel. Yeah, so you can have a look into the lecture notes and you can do it again. So this is the formula for the piano kernel. So because the rule has degree precision 3, so that's why you have power 3 here divided by 3 factorials. Yeah. And because in this case, t is strictly less than the midpoints. Okay, so then you can include the midpoints and the right point B. Yeah. Okay, so that is the, so this is the error, you know, I mean function. Yeah, so you plug in the quadrature a plus b over 2 here, and then you plug in the quadrature b here. Yeah, and this integral is a bit complicated, but it can be done. Okay, so I think I just wrote down the results here, but you can do, you know, a few more steps to get out this. Yeah, and then if t is bigger or equal the midpoints, then you can take only the point B. Yeah. Okay, so t here is strictly less than the midpoint, and t here is greater or equal to the midpoint. Then you take only the point B, and then you get out this. Okay, so then in the end, you can get out the errors. So the errors is just the integral of kt, and again, this is lengthy integrals, but it's not very hard, and at the end of the day it will be of this form. Okay, so we are not going to repeat it in the tutorial. And now, yeah, so this one is the errors. Yeah, so the errors is integral of kt, the fourth derivative of the function f. Okay, and now this is the this formula again. Well, we want to derive it at least from the theory. Okay, and now you go back to the, okay, so now let me write down on a piece of paper. So you have you have the integral, yeah. So assume that the integral, the exact integral, yeah, equal the numerical quadrature of step size h, okay, plus a constant time h to the row, yeah. So row is the order of conversion, yeah. So then now how do I prove s to h minus sh equal some constant 1 minus 2 to the row h to the row? Well, okay, so now if you use this formula, but for a quadrature with step size 2h, yeah, then you got this one, it's just 2h to the row, okay? And then you just take the difference. So if you take 1 minus 2, then you get 1 minus 2 is 0 is sh minus s2h plus c h to the row 1 minus 2 to the row, right? Okay, and you can move s to h to the left, yeah, and you get ch row 1 minus 2 to the row. Okay, so that is the first identity. And now we have to deduce the formula for row. Okay, so the formula for row has S for H as well. So you have S for H. So maybe I should put I equal S for H. Yeah, plus C for H row. Yeah. Okay, so now I'm going to take, so this is my 4. Okay, so I'm going to take 4, or maybe I take 2 minus 4. So 2 minus 4. Then 2 minus 4, then I just have 0 on the left, yeah. And then you have S2H minus S4H. Okay, so S2H minus S4H plus the constant C 2H. Now 2H to the row can be the common factor, okay? And then you got 1 minus 2 to the row. Okay, so 2 to the row multiplied by 2 to the row is 4 to the row. And then this one give you S 4H minus S2H is approximately C2H row 1 minus 2 to the row. Okay. And now I just take number 3 divided by number 5. So if I take, so this one is my number 3, yeah. Okay. My number 3 here. And this is my number 5. Okay, so I take 5 divided by 3. Then the constant's gone. Yeah, the constant's gone. 2 minus 2 rows go on. So what you have left is just 2 to the row. Okay. So if you take the ratio, then you got S2H over S2H minus SH row logarithm of 2. And that's it. So that is the one that, you know, you divide it by logarithm 2. You get our rho. Okay. Yeah. And now what is the next question? So the next question is, suppose I want to find out the constant C. So we got up to this formula, yeah. So now suppose I want to find out the formula for the constant C, yeah. Then we go back to the formula we derived for S2H. So if you go back here to this formula, then you can write down the formula for C, right? So now if I take 3, then I will have C is just equal S2H minus SH divided by H rho 1 minus 2 to the rho. Okay. And if you know rho equal 4, you know, suppose for Simpson rules, you know, suppose you know rho equal 4, then C is just equal S2H minus SH over H to the 4 1 minus to the 6 minus 15. Yeah. Okay, so this is exactly the formula. So the formula is SH minus S2H over 15H to the 4. So just the same, yeah. Okay. And that is question 7. So any questions so far so good? Everything is very clear, yeah. Okay, so number 8. So go back to the question, yeah. So now if I'm going back to the question, show that if f double prime is positive, okay, then the integral, the exact integral, is in between the midpoint rules and the trapezoidal rules. So in effect, the trapezoidal rule is an upper estimate, and the midpoint rules is a lower estimate. Yeah. So why is that? And you can test with the e to the x. So why is the case? So what does it mean when f double prime is positive? What does the curve look like? Yeah, so yes, concave up. Yes, very good. Yeah. So when concave up, then you can see that, I mean, from the pictures. So suppose I have function concave up like, say, x squared, right? So suppose I have x squared, y equal x squared, yeah. And I integral, say, from -1 to 1, yeah. Well, maybe -1 to 1 is so symmetric, maybe -1 to 2. Okay. And you can see that suppose I have only one subintervals, yeah, then the trapezoidal rules look like this. Okay. So you see that the trapezoidal rules give you a bit more than what you needed, because you know the area is here. Yeah, and the trapezoidal rules give you an upper estimate. Okay, but the midpoint rules question, yeah. I did not see for previous exam paper. No, we haven't worked out that answer for previous exam paper yet. Maybe next week. So when we finish with the project and when people, start to think about the final, then we will work on the final exam papers. Okay. Yeah. Okay. So, but now, what is the problem? So back to the problem. Yeah. So the problem say that, okay, so the exact integrals will be less than the trapezoidal rules. Yeah. So the midpoint rules. Okay. So the midpoint rules is, so it's not easy to see. Yeah. So the midpoint rules is, suppose you got, so this one is 1 and 2, right? So maybe the midpoint is somewhere here. Yeah. So the midpoint then give you this area. Okay. So the midpoint rules give you this area. And it's not easy to see why, the midpoint rules give you a low estimate. So it's not easy to see it. But it will be less than the exact integrals. So how do we show it? Like more rigorously. So how do we show that rigorously? So this one could be a very good question. Yeah. Some stuff up to compare. Yes, essentially that is the case, but we have done it already. We have done it already. So if you remember the errors, yeah. So now suppose I take the errors of the midpoint rules, yeah. Is the integral of f minus the midpoint rules, yeah. Then, well, the midpoint rule with step size h, then what is this equal to? So what is the errors of the midpoint rules? So we did it just a few, maybe like 20 minutes ago. So what is the errors for the midpoint rules? So did we do it in question 1? Yeah. Yes. So it will be b minus a over 24 f double prime c h square. Yeah. And we know that f double prime is positive. B minus a is positive. H square is positive. So the whole thing is just are not positive, greater or equal 0, right? Yeah. So therefore, well, essentially this one is the errors. Yeah. So therefore, you just have the exact integral is greater or equal the midpoint rules. Yeah. So this is one of your inequality. Okay. So we prove it already. Yeah. So now we just use it. Okay. And we prove it. There's a lot of complicated proofs going on, right? We have to use Peano kernels and mean value theorems and mean value theorem for integrals. Yeah. But at the end of the day, we got this results already. We just use it. Because otherwise it's not easy to prove it from scratch. Yeah. And then you have the same for integral minus the trapezoidal rules. Okay, so what is the formula? What is the formula for errors of the trapezoidal rules? Well, I mean, you just need to look it up, yeah. But it will be, so what is the formula? we did it in the question number 3. Yeah. Yes. So minus b over a over 12 f double prime c h square. And you see you have minus here, and this one positive. One positive. So this one less or equal 0. Yeah. So therefore you have integral of f is just low. It's just smaller than trapezoidal rule applied to f. So this is true for all the partition. Okay. So and true for all concave up functions. So very general results. Yeah. And we just use the theorem. Okay. But the theorem requires you to prove, you know, like a lot of stuff already. And so now, let's see whether we have time for the last question. Well, so this one is just like, you know, a special case when you have an improper integrals. Yeah, so improper integrals. So first you estimate the tails, and after that, you know, I mean, you estimate how many intervals you choose to get the error. So maybe let me put in the solution. Yeah. And so this one is similar to question 1. So that's it. So maybe we stop here. Yeah.